All right, we're on to lecture 25, part B. So in the last one, we talked about, hey, intermolecular forces, they tell us all about the way a molecule's going to behave. They control whether you boil easily, whether you evaporate easily, whether you have a high or low surface tension. All kinds of properties have to do with these forces. So what are these forces? Well, we're going to learn about in this video, there's actually three kinds of intermolecular forces. And so we're going to learn what are they, what are the three types of intermolecular forces, and how can you tell if I give you a molecule which force is going to be present between these neighboring molecules. It turns out it's going to have a lot to do with polarity, so that's going to be sort of something we're going to talk about again. All right, with that, let's go ahead and get started. What are these intermolecular forces, and how can you tell what you'll have in between molecules, which one you'll have in between molecules? Okay. Force number one, possibility number one. There are three types of intermolecular forces. The first are called dipole-dipole forces. So when do you get these? Basically, they're going to occur. It's between polar molecules. So it's an attraction. It's an attraction between two polar molecules. So all polar molecules will be held together with their neighboring polar molecule by a dipole-dipole force. All right, so let me show you a little example of that. So I'm going to draw up a polar molecule, and then we're going to see what's going on exactly. So I think this guy right here, let's start off with this guy, CH, and we'll draw him out here. So this is actually CH3F. All right. So, the F would still have a bunch of lone pairs on it. All right. So, as I mentioned a little while ago, kind of the key to these intermolecular forces, it really has to do with polarity. So, first off, let's just make sure, I think this is a polar molecule, but let's make sure I'm right about that. So, how do you know if you have a polar molecule? Well, first thing you got to do is you look up the electronegativities. So, I'm not going to put up the table. Let me just tell you, if you looked up the electronegativities, fluorine is 4, carbon is 2.5, and hydrogen is 2.1. So in all polar molecules, there's a polar bond. In all polar molecules, there's a polar bond. So I want you to think about, in this molecule, which one is the polar bond? Is it the bond between carbon and fluorine? Is that a polar bond? Or is it the bond between carbon and hydrogen? I guess all three of those would be the same. So which bond is polar? The CH bond or the CF bond? Which one's polar? Oh, it should be the CF bond. So it's the CF bond, and the way I know that is because if I subtract, you get, well, let's do it down here. 2.5 minus 4, you get a difference of 1.5. Anything over 0.5 is a polar bond. If we try the other one, by the way, 2.5 minus 2.1. When you subtract here, you only get 0.4. Oh, that's not enough. It has to be 0.5 or more to be polar. All right, so our polar bond is the bond, I'm going to erase this, between the carbon and the fluorine. And so what does that lead to? Well, when you have a polar bond, that leads to charged areas forming inside of this molecule. So to be a little bit more specific, the fluorine, because it has a higher electronegativity, the electrons are going to go towards the fluorine. The fluorine would become a little bit negative. The carbon, which is losing the battle over those electrons that it's sharing, if you're losing electrons, you're going to become a little bit positive. All right. So yeah, this molecule is polar. It has a polar bond. And yeah, the other requirement, remember, was a lone pair on the middle atom, or different atoms attached to the middle atom. We have different atoms attached to the middle atom. So that's why it's polar. Polar bond and different atoms attached to the middle atom. So yeah, that's a polar molecule. Now, we're not really talking about what's going on inside of a molecule in this chapter. We're talking about what's going on between molecules. So let me draw up another one. I'll draw it down here. And let me draw it again. So this would be like a neighboring molecule of, the same thing. Now, what we just talked about, that's going to go on inside of any molecule of CH3F. So the fluorine, winning that battle, becomes a little bit negative. the carbon, losing that battle, becomes a little bit positive. So we have charges inside of these molecules. So because there's charges inside of these molecules, they're going to be sticking to each other. They're going to be attracted to each other. So I could draw that attraction more than one way. But for example, the fluorine, the negative fella in one molecule, would be attracted to the carbon, the positive fella, in the other molecule. So that would be your intermolecular force, and specifically it's called a dipole-dipole force. Dipole-dipole force. It's the attraction between two polar molecules. To be a little bit more specific, dipole-dipole force, that's a little messy, sorry about that. To be a little bit more specific, it's basically the positive of one molecule, carbon in our case, is attracted to the negative in a neighboring molecule. All right, with that, let's move on. All right, so that's our first kind of intermolecular force. This happens when you have polar molecules. It's called dipole-dipole forces. All right, there's two more to go. Let's flip over. We'll move on to the next one. Okay, our second type of intermolecular force are called hydrogen bonds. So let me tell you a little bit about them, and then I'll show you an example. So hydrogen bonds are basically just a special type of dipole-dipole force. All right, so it's going to still involve like the positive of one molecule being attracted to the negative of a neighboring molecule. Now, what makes it special? Well, the reason why it's special is that it's very strong. It's the strongest kind of intermolecular force. And then the other reason why it's special is that it only occurs in a few possibilities. So it occurs, we'll say, between molecules that contain, oops. All right, you have to have this as part of your structure. And either a bond between carbon and hydrogen, nitrogen and hydrogen, or fluorine and hydrogen. All right, now if we look at those bonds, let me point out to you something about them. So I really want to think about whether these are polar bonds or non-polar bonds. So the way I would know that, right, is I would look up the electronegativities. So let me go ahead and put them down for you. So oxygen is 3.5, hydrogen is 2.5, nitrogen is 3, hydrogen is 2.1, fluorine is 4, hydrogen is 2.1. All right, so there's 3 bonds up here. A bond between oxygen and hydrogen, nitrogen and hydrogen, fluorine and hydrogen. Let me ask you, are they all polar bonds or are they all non-polar bonds? They're all polar bonds. They're all polar bonds. Why? Because if I subtract electronegativities, we get a number bigger than a half. 1.4, 0.9, and 1.9. So they're all polar bonds because we have a bigger electronegativity, bigger than 0.5. Now let me ask you one other question. If they're all polar bonds, that means we're going to have charges forming. The hydrogen in all of these, is the hydrogen going to become a little bit positive or a little bit negative? Oh, the hydrogen's losing the battle. He's got a lower value. If you're losing the battle for the electrons, if they're moving away from you, you're going to become a little bit positive. The hydrogen's going to be the loser. It's going to be a little bit positive. The fluorine and the nitrogen and the oxygen, they have the bigger value. They're going to become a little bit negative. All right. So with that, you get these forces, you get these charges, and that's going to lead to attractions between molecules. All right, and they tend to be really strong. So if you see an OH bond, an NH bond, or an FH bond inside of a molecule, that means we're going to get a hydrogen bond to its neighboring molecule. Let me show you an example. An example of where this happens is actually between two water molecules. All right, so two water molecules. If you have water, water molecules are going to stick to each other. And the way they're going to stick to each other is called a hydrogen bond. So I don't know, I don't want to maybe rewrite everything I just did because it might get a little messy. But, you know, as we just talked about, what's going to happen, we're going to get charges. Hydrogen is going to become positive because it's losing that battle with oxygen. Oxygen is going to become a little bit negative. Now, I could do more than that, but that's like one case where that happens. And in our neighboring water molecule, we'd have the same thing going on. The oxygen is going to become negative. He's got the higher electronegativity. The hydrogen is going to become positive. That would also happen over on this side too, wouldn't it? So there's lots of charges, and any positive will be attracted to any negative. So where do I draw that attraction? Anywhere, really. Any positive to any negative. For example, this oxygen is going to be attracted to the hydrogen in that molecule. So that attraction again between neighboring molecules, that's called a hydrogen bond. Hydrogen bond. Okay, so this will happen again whenever you see in the molecule OH, that's what we have here, or NH or FH. If that's part of the molecule structure, you will get hydrogen bonds with its neighbor. All right, with that, one more kind of intermolecular force to go over. All right, let's flip over and we'll move on to our last possibility. Okay, so with that, we've talked about two forces and they both have occurred between polar molecules. So what's going on in between nonpolar molecules? There has to be something. So in between nonpolar molecules, you're going to have dispersion forces. All right, so dispersion forces are, first off, very weak. They're the weakest kind of intermolecular force. So they don't really do a very good job keeping neighboring molecules together. Let me kind of read this, and then I'm going to talk about an example here. They're kind of the weirdest one, the one that's the hardest to understand, actually. So first off, they occur between all molecules, but they're most important for nonpolar molecules. I'll explain more about that in a minute. Their strength increases, so they're all weak, but their strength increases with, I guess we'll say it this way, molar mass. So the size of a molecule. So dispersion forces are always weak, but if you're bigger, you'll get a little bit stronger. The bigger the molecule is, they'll get a little bit stronger. All right, so what are these dispersion forces? Well, they're the attractions between temporary charges that form due to the random movement of electrons. They're attractions that occur between temporary charges that form due to the random movement of electrons. All right, that might be a little confusing. What does that mean? Well, let's do a little example. A little example would be like helium. So if you have a bunch of helium atoms, what's going on to keep helium atoms attracted to each other? Is there anything? Well, there is. Now, before I can talk about it, let me just remind you, helium, if you look at your periodic table, it's element number 2. That means it's got 2 protons and 2 electrons. It's got 2 protons and 2 electrons. So let's imagine we could take a picture of a helium atom, all right? And let's start off with this picture on the far left. Now, in that helium atom, there would be 2 protons in the nucleus. Oh, that color isn't too good. Let's do a different color. What's going to show up? Maybe red. 2 protons in the nucleus. That's kind of the thing in the middle. And there would also be 2 electrons moving around. All right. So as far as this atom goes, those electrons aren't going to stay put. Right? They're always moving around. So if we took a picture at one moment, we might find them like this. You notice one of the electrons is kind of like on the top side of the nucleus, and one electron's kind of on the bottom side of the nucleus. So those electrons are kind of spread out. So they're spread out kind of evenly. Now, they're not going to stay there though, right? They're going to move around. So let's imagine a second goes by, a millisecond goes by, whatever, and we take another picture. Well, let's say now those electrons have moved a little bit, haven't they? We still have the protons in the middle, and one electron's like on the top left, top right, I guess, and the other one's on the bottom left. So the electrons, again, are kind of evenly spread out. Like one's up on the top side and one's down on the bottom side still. Now, again, they're not going to stay there. They're going to keep moving those electrons. So the electrons, they're doing whatever they want to do, right? So at some moment, maybe another millisecond goes by, we look at the atom, and this is what we find. The nucleus, yeah, the protons, they're kind of staying where they are. But the electrons, just by kind of random chance, they've both moved over to the left side. They can do whatever they want. They both went to the left side. So because they're kind of in the same area, that area is going to become a little bit negatively charged. So the left side of the atom has all the electrons. It gets a little bit of a negative charge over there. Now, the other side of the atom, the protons are still kind of more on the right-hand side. So this area is going to become a little bit positively charged. So at this one split second, the electrons moved into one spot, it made it negative, and then the spot they left became a little bit positive. But this doesn't stay this way. So in a dispersion force, the electrons, they do that, but then they spread back out. And when they spread back out, the charges disappear. And then they stay spread back out, and the charges disappear. But then, maybe a second later, they happen to congregate. And when they get into the same area, we get charges, negative charges. So that's kind of what this is going on here. They're the temporary, so they don't stick around. They're the temporary charges that form due to the random movement of electrons. So as they move around, we get charges forming, but just for a second. All right, so because these charges aren't always there, they kind of come on and then they go off. That's one reason why they're really weak. All right, so we'll do a little summary of these forces in a minute. But yeah, they're always really weak. Okay, so let's summarize these intermolecular forces. So I have a chart. Let's flip over to it. Okay, so this chart kind of goes over these three types of intermolecular forces. Now, I should say it lists them in a little bit different order. I kind of went through them in the order that I hope made the most sense. But this lists them by strength. So the weakest kind of intermolecular force are called dispersion forces. You might also hear them called London forces. Okay, that's another word for dispersion forces. They're the weakest. They occur actually between all molecules. So all molecules have electrons, so we can get these temporary charges. So they're actually present in all molecules, all atoms and molecules. But when you think about them, you're going to think, well, they mainly have to do with nonpolar molecules. Now, why? Because nonpolar molecules, it's all they have. It's the only one they have. It's all they have. It's the only kind of intermolecular force they have. Now, if you're polar, yeah, you're going to have dispersion forces, but you actually have something even better, even stronger. And that is called the dipole-dipole force. So these are like moderate strength. They occur in between polar molecules. So polar molecules have an even better attraction, an even stronger attraction. That's called a dipole force. All right. Now, the strongest of all is hydrogen bonding. Hydrogen bonding is the strongest, so it's going to keep neighboring molecules the most closely connected, the best connection between neighboring molecules, the strongest connection between neighboring molecules. And it only occurs when you have inside of the molecule, you see, when you draw out the Lewis structure, an HF, or when you draw out the Lewis structure, you see an H. I'm flipping the order here. Let's do this better. An HO or an HN. So if you have one of those as part of what you are, you can hydrogen bond to your neighbor. All right, so understanding the strength of these intermolecular forces, that kind of helps us understand those properties we talked about in the first part, right? So if you have strong intermolecular forces like hydrogen bonds, you're going to be hard to boil. If you have strong intermolecular forces like hydrogen bonds, you're going to, not evaporate very quickly. If you have weak intermolecular forces like dispersion forces, you're not really stuck to your neighbors. So you boil easier, you have a lower viscosity, all those things that we talked about. All right, so with that, let's do a few practice questions on this topic. Let's do a few practice questions to see if this is making sense. All right, so really what I want you to be able to do is if I give you a molecule, I want you to be able to figure out what kind of attractions are going on between neighboring molecules, okay? So as you've kind of seen, the whole key to this is understanding polarity, honestly, because polar molecules do one thing, non-polar molecules do another thing. So you got to know whether a molecule is polar or not. And then once you know that, you can figure out the kind of intermolecular force. All right, so let's do a little example here. So it says, tell me the strongest type of intermolecular force between carbon dioxide molecules. So the first thing I got to do is I got to figure out whether carbon dioxide is polar or non-polar. So how do you do that? Well, the way you do that is, first off, to be polar, you got to contain a polar bond. So let's look. How are you going to figure that out? Oh, you need your electronegativities, don't you? 2.5 and 3.5. So the bond, let's look at this carbon-oxygen bond. And I know it's a double bond. That doesn't matter. So the attraction, or the electronegativity difference, I should say, between those atoms is 1. So if you have a difference of 1, that makes that bond polar. This is a polar bond. All right. I could look at the other one. I'd get the same answer, wouldn't I? So if you looked at this bond over here going to kind of the left of carbon, again, you get the same thing, right? 3.5 with 2.5, that difference is 1. Yeah, it's also polar, right? They're both polar bonds. So to be polar, you got to contain a polar bond and a lone pair on the middle atom. Do you see a lone pair on the carbon? I don't see a lone pair on the carbon. Or a polar bond and different atoms attached to carbon. That's not true this time either. We have oxygen, carbon is bonded to only oxygen. Those two atoms are identical. So I couldn't find the lone pair. I couldn't find the different atoms. That means that this molecule, even though it has polar bonds, is actually non-polar overall. All right, so what do non-polar things do? Non-polar things are held together with their neighbor by the weakest kind of intermolecular force, dispersion forces. So it should be A. So you'll have dispersion forces between carbon dioxide molecules. All right, let's do one or two more. Let's see if this is making sense. Maybe I'll get you to help me a little bit with the next ones. All right, so another example, formaldehyde. The structure of formaldehyde is shown below. What's the strongest type of intermolecular forces in formaldehyde? So to know what you got to know whether this thing's polar or non-polar. So how are you going to know that? Well, you're going to look up the electronegativities. I'm going to tell them to you just to save us all a little hassle. All right. To be polar, you need a polar bond. Is there a polar bond? Yeah, there is. It's the bond between carbon and oxygen. The carbon-oxygen bond, again, it's actually what we saw in the last molecule, right? 3.5 and 2.5, that bond is polar. I could check the other bonds, carbon and hydrogen, 2.5 and 2.1. This bond would be non-polar. And so would this one, 2.5 and 2.1. So that one also would be non-polar. So as far as that goes, yeah, there is a polar bond. There is a polar bond, specifically the carbon-oxygen bond. Now, beyond that, I also need to find, to be a polar molecule, a lone pair on the middle atom. Nope. Or different atoms attached to the middle atom. Yep. There are different atoms attached to the middle atom. Hydrogens and oxygens. That's what I mean by different atoms. So we found a polar bond and different atoms attached to the middle atom. That makes this thing polar. All right, now, the question I have for you, though, the kind of new question, is what is going to be the intermolecular force? So what is the intermolecular force? Polar bond, polar molecules will do dipole-dipole attractions, like the medium strength attractions. All right, so this thing, if you're polar, you're going to have dipole-dipole forces between you and your neighbor. All right. So with that, let's try one more. Let's try one more. Let's see. Let's try one more. Let me give you one more to think about. Let me flip over. All right. This one, I don't know. It may not help you much at all. Let's see if you can figure it out. All right. The structure of ammonia is below. What's the strongest kind of intermolecular force? What's the strongest kind? I should mention, if you're wondering, why do they say strongest? Remember, as I talked about earlier, everything has dispersion, but I really want to know what's the strongest type. So what's the best kind of intermolecular force? All right, now this one actually, ammonia, I have the Lewis structure there for you for ammonia. You might notice something kind of important. Look at it really carefully. And you know what? I'm not even going to tell you the electronegativities. Let me see if you can think about it. We'll go over it. Oh, this is one of the ones that has that special group of atoms. If you are a molecule with an FH or an OH or an NH as part of who you are, you hydrogen bond with your neighbor. So this guy should be able to hydrogen bond with its neighbor because it's got NH as part of its structure. We could figure out it is polar and all that. That's true, and that's not bad to know, not bad to realize. But if you see any of these three as part of the Lewis structure, you don't really need to worry about polarity or non-polar or any of that stuff. Just go, oh, that's got to be hydrogen bonding, because you see that as part of the structure. All right, with that, I hope this makes sense. We're going to stop for part B, and that's actually it for this lecture for 25. It's a little short. Like I said, this chapter is not quite as much detail in it as maybe the last one. So if you're having any issues or questions, you can contact me, and I'll be glad to help you out. All right, with that, let's go ahead and call this one good, and I will see you again soon. Bye-bye.